Okay, good morning. So let us continue our discussion about the cross product by starting a simple and good example. Let u and v be vectors. Determine a relation between the norm of these three vectors u, v, and u cross v and u dot v. Yes? Of course, all of them are scalars. They are numbers. We want to find a general relation between them. It's good to know about it. So how we can do that? So here, if you remember from yesterday, so I would say let theta be the angle between u and v. Yes? So now, if I ask you what is the norm of u cross v, it's from the definition is the norm of the first vector multiplied by the norm of the second vector multiplied by sine of theta. This even works if u and v are zero vectors, because in that case the left hand side becomes 0 and one of them is 0, the right hand side is also 0. And now if you see u dot v was the previous lesson, so it becomes norm of the first one, norm of the second one, multiplied by the cosine of the angle between them. Yes? Okay, I want to find a relation between these four numbers. So these four numbers appear here, but I do not need theta. Actually, theta was not given in the problem from the beginning. I bring it in because I wanted to write the formulas, but I have to get rid of it at the end, because I want to find a relation between them. So what should I do? How should I get rid of theta? I want to find a relation in which theta does not appear. Because if I can do that, then I can find a relation between the numbers which is demanded in the problem. So the only disturbing part is theta. I have to get rid of it. How should I do that? Ideas? So if I want to get rid of sine and cosine, there is one famous formula in trigonometry, yes? And that's sine squared plus cosine squared is equal to 1, yes? The point is that I do not have sine squared, I do not have cosine squared, but that is easy to manage, yes? I raise both sides of this one and this one to power 2. So then what happens here? So you get norm of u cross v squared is equal to the norm of u squared, norm of v squared, and then you have sine squared theta, but then this becomes equal to, okay, so let me write it in this way, and then I have u dot v squared is norm of u squared, norm of v squared, and then cosine squared theta, yes? But I want to get rid of theta, and then I am lucky that these two factors are exactly the same. So if I add them, I can factor this out, and then sine squared plus cosine squared becomes 1, and then I'm done. Yes? So then it becomes norm of u cross norm of v squared. If I add this one to this one, this factor can be pulled out. I'm sorry, I forgot to add the second one. This one plus this one. This becomes this one and then I will have sine squared theta plus cosine squared theta, yes? But we know that this is exactly 1, so I actually found my relation. Yes, that is a relation between only these 4 numbers demanded in the problem. So, and usually people move this to the right, and this is what is called Lagrange identity. And Lagrange is actually a French mathematician, yes. So yes. Yeah, good to know about this. So you have this relation. On the one hand, you have the cross product. On the other hand, you have the dot product. So that would be the relation between. Yeah, is that clear? Have I made a mistake? Okay. Now I want to write a theorem here. So let me change my colors alternating. So let me write theorem. So that's an extremely important theorem. I want to list the properties of the cross product, and I expect you to remember them. Yes. So I would say let U, V, and W be vectors, and let alpha be a real number. Then, okay, so number 1, okay, you tell me, what happens if I cross product a vector by itself? What's the answer? You need to imagine. Do you remember what was the cross product? Yes? I want you to remember the definition. So if I cross product a vector by itself, what is that? It is 0. It was defined. Do you remember that experiment? So what kind of 0? The 0 vector. Let us compare this one to refresh your memory with the dot product. So do you remember, if I had a vector multiplied by itself using the dot product, what was the answer? Norm of the vector squared. So it's good to compare them, yes? So they are quite different things, yes? So u cross u is the 0 vector, but u dot u is the norm of the vector squared, if you just want to compare and remember it. Okay, number 2, if I tell you that the cross product of 2 vectors u and v turns out to be the 0 vector, what you can conclude from this? Yes?
The first one is 0, the second one is 0, or it doesn't matter.
How? Exactly. So it means that the first one is the 0 vector, or the second one is the 0 vector, or U is parallel to V. And of course, this arrow goes in both directions. Okay, so let me refresh your memory. Before studying the cross product, if I want to show that two vectors are parallel, we had a method to do that. What was that? Do you remember? I wrote it as a remark somewhere at some point. If you want to show, before studying the cross product, if you wanted to show that two vectors are parallel, what is the general method to do that? You were supposed to show one of them is a multiple of the other one. Is that right? So please remember, both of them are being necessary for us. So if you want to show that two vectors are parallel, of course, to being parallel makes sense, the vectors shouldn't be zero. So assume that you have two non-zero vectors and you want to show that those vectors are parallel. Before studying the cross product, we had a method to do that. We have to show one of them, any one of them, is a multiple of the other one. But there is another alternative here. If you want to show that two vectors are parallel, then an alternative method is to cross product them and show that the cross product is the zero vector. This is good because if you want to say something about vectors being parallel, you need to remind yourself about the cross product. If you want to show that two vectors are perpendicular, you need to remind yourself of dot product. So have this connection in your mind, okay? Perpendicularity, dot product, parallelness, cross product. Yes? Remember these things in this way. Okay. Then yesterday we also discovered this, yes? We discovered that this operation is not commutative. But it is not that we cannot say anything. We actually can say a very nice thing. We can say that U cross V and V cross U, of course they are not equal, but there is a very nice relation between them, and one of them is negative of the other one. So it means U cross V and V cross U. Do you remember the reason behind that? If you have forgotten, you can just review the video. I don't want to spend time on it again. But U cross V is always negative of V cross U. So you can swap them, but you have to remember you have to put a minus sign. But in the dot product, if you remember, I don't need to be careful at all. U dot V and V dot U are exactly the same. Yes? Do you remember when I was talking about dot product, I asked you about associativity of the dot product. Do you remember what was the point? So something like this. Yes, do you remember? I talked about this, but this is completely meaningless. So we cannot ask if this is true because V dot W is a number. You are not allowed to dot product a vector by a number. So this is totally meaningless. So this is why the dot product, asking about associativity, is meaningless. But what about cross product? Do you think it still is meaningless or meaningful? Let us check. If I write U cross V cross W, this is not meaningless anymore. Yes, because V and W are vectors. When I cross product them, what happens? It becomes a vector, and this one is also a vector, so that's meaningful. So this expression is meaningful, that expression was meaningless. So the notion of associativity is lost when we go to dot product. But it might be true for cross product, yes? It might be true that this is the case. Yes, so it is not meaningless. It is meaningful to ask this question, but it is false. Okay, we will come back to it. So for the time being, we don't have associativity for the cross product. So this is extremely important. I cannot ask you to calculate this for me. This is ambiguous. Because if I ask you to calculate this, you have two cross products. I have myself prioritize which one you have to do first. Because the associativity is lost. Even though it is meaningful, but it is not true, it's false. Yes? We come back to it a little bit later. Okay, so let us go to the next one, 4. So number 4 is very similar to what we had for the dot product. So if I have a number alpha, if I have two vectors u and v, if I cross product them, it becomes a vector. And if I take this vector and multiply it by a number in the meaning of multiplying a number by a vector, it doesn't matter if I do it, if I cross product them first and then multiply by my number, or if I multiply the first vector by alpha, produce you a new vector, and then take this vector and cross product this by v, or even it doesn't matter if I multiply my number by the second vector and then multiply this u. But I have to keep the order. U is always on the left, v is always on the right, so I'm keeping u on the left, v on the right all the time, yes? So do you remember, this was exactly the same thing for the dot product. So I mentioned that actually this coefficient, this numerical coefficient is floating. So it can float into u, next to v, or outside. So it doesn't matter how you calculate it. That is exactly the same scenario we had for the dot product. Do you remember? If I have u alpha times u dot v, but of course here, this is the dot product. This one is the normal primary school product, yes? Because that's a number, that's a number. But here, u cross v is the vector, alpha times this one is the multiplication of a number by a vector, yes? So that's different. But anyway, that was true here, if you remember. This is also true here. So that is very instructive to understand the differences and similarities. Another one, which is hard to prove, we skip for the time being, and that is even though we lose commutativity, we lose associativity, but we do not lose distributivity. That's very nice, yes? So it means that if I have u cross v plus w, I can distribute it. The proof of this one is harder, so let me write consistently. So if you remember, I didn't even prove this one for you for the dot product. We can, at some point, I can come back to it and prove them, but for the time being, let us not spend so many time on it. Of course, if you want, I can emphasize that if this is also a minus sign, you can also have a minus sign. But order that you distribute is extremely important. So here you only have to, so u is on the left, you have to keep u on the left all the time. So here in the dot product, I don't need to be careful, even though most of the time in the dot product I do this, yes? U dot v plus w, I distribute it as u dot v plus u dot w, but I don't have to, yes? I can write it as v dot u or w dot u, yes? Because it's commutative. Even though, of course, most of the time I write this, but if I write this, this is not wrong. But if you write the other way around, it would be wrong for that. Yeah, so be careful. So if you distribute from the left, you have always to distribute from the left. So let me write an alternative here for you. So if you have v plus w, and then multiplied by u, and you want to distribute it because now u is sitting on the right, you should keep it on the right all the time. So it becomes v cross u plus w cross u. Yes? So you have to distribute either from the left or from the right. So you remember that usually when we go from this direction to this direction, we call it distributivity. But if I go from this direction to that direction, we say that I am pulling that common factor out or factoring out. Here, you don't need to be careful, but there you have to be careful. Yes? So for example, so let me write example. In each case, factor u out. So for example, if I give you this, u cross v plus u cross w. Number 2, u cross v, v cross u, w cross u, and the third one, u cross v plus v cross w. U cross w. No, w cross. Sorry. Yes. So if I insist you to factor u out, there is no problem here. Yes, u and u are common factors. Of course, factors are for numbers, but you understand what I mean. And u cross is sitting on the left in both of them. So you can pull it out, but you have to pull it out from the left. Yes? So then it means that this becomes u cross v plus w. Here, the common factor is actually sitting on the right. I can't do that, so I have to pull it from the right. So what happens? It becomes v plus w, and then I have to pull it out from the right. From the right hand side. But here, one u is on the left, one u is on the right. I cannot pull u out immediately. I have to adjust it, okay? So I have two methods. I have two alternatives here. I can keep u cross v here, but I have to make this one on the left if I want to pull it out. But I have to swap them, but the price that I have to pay is to make it negative. Then u in both of them is sitting on the left, so I can pull it out from the left. So that is correct. Or we can do this alternative here. I swap them. Then I pull u from the right, yes? Yeah, so remember these very simple differences, otherwise you will be in trouble. Okay, so I don't know, let me write some expressions. For example, if I want to write A cross 3B, what can I write? I can write it as simply 3A cross B. So I want you to realize that there is no difference between these two writings because of what? And of course, here, because of this property, I really don't need to be careful to prioritize this. Yes, because it doesn't matter if you do this one first and then multiply it by it, or you do this one first, or you do that one first. So if that is the case, this is not ambiguous at all. Alpha, u cross v, and usually you see it in this form in the books, without putting pair of brackets, because it is irrelevant. Whatever you interpreted, the answer would be the same. So from now on, this is a very nice combination. How you interpret it, it doesn't matter. You can interpret this one first, then multiply it by 3. You can interpret it this one first and then multiply it by b. Or you can interpret it as 3 multiplied by b, then a multiplied by that. So what do you think would be the answer to this? What is this one? Yes? A zero vector. Yes, you can interpret it in different ways. You can say that 1/2 a is parallel to a. 3a is also parallel to a, so it means that these two have to be parallel to themselves. And if I have two parallel vectors, when I cross product them, it becomes the zero vector. Or, if you want to, you can, these are scalars, they are floating around, so I can write it as 3/2 and then a cross a, but that is the first item. Any vector cross product by itself is the zero vector, so it becomes 3/2 times the zero vector, but of course that's also the zero vector. Yes? So I think these are actually simple things that you can do. For example, what do you think about this? A cross product, I don't know, by 2a minus 3b. What can I do, for example? I can use distributivity, so I can write a cross 2a minus a cross 3b. Okay, if I want to simplify, what is the answer to this? Is the zero vector, and then I can write, if instead putting 3 here, I can put 3 here, so it becomes minus 3a cross b. And if you don't like minus signs like me, so you can just write it positive and interchange them, yes? But that's not compulsory. So if you want to simplify, that's one way. Okay. So let me give you one example. This is very simple and wait for you a little bit. Yeah, this is very simple. We want to practice a little bit of simple algebra between vectors using the cross, which are involving cross products. Okay, so example. So simplify as much as possible. Okay, number one. Yeah, this is simple. U plus V plus W cross product by W plus U plus V cross product by V, and then U cross product W minus V. Okay, so you start doing that. It's very, very simple algebra. And I will write you one more. Did you get the answer for the first one? Yes?
I got, for the first one, 2u cross w.
Yes, yeah, apparently it's correct. So number one, we start using the distributivity, but I have to distribute always from the right. So this becomes U cross W plus V cross W plus W cross W. And then the next one, plus I distribute this one inside, U cross V, V cross V, and then we have W cross V. And then I will distribute this one, but this time from the left. It becomes U cross W minus U cross V. Yes? Of course, this one is the zero vector. This one is also the zero vector. Okay, then what? I have U cross W here. I have another U cross W here. So they will add to 2, yes? 2U cross W. And it is not ambiguous if I write it in that way. We learned about that. But what can I do? U cross V minus U cross V are cancelled. What happens between these two? One of them is U cross W, the other one is W cross V, so I'm adding them so it becomes again 0. That's the answer. Number 2, I just distribute it. I multiply this by that, so it becomes 2U cross W minus 2U cross 2U, and then minus 3V cross W minus 3V cross 2U. And then this one plus V cross 2U, V cross V, minus V cross W, minus 2W cross 2U, minus 2W cross V, minus 2W cross W. Okay, so let us simplify it. And please watch me if I am doing something wrong. This one is 0, yes? Is there any other thing? Yes, that one is also 0, the 0 vector. How we can simplify? Do I have UW? U and W. Do I have somewhere else? I think this is the only one, yes? U and W. Here we also have UW, yes. So this becomes minus 4WU, but this is UW, so it becomes negative 2UW, yes? Am I right? So I take this one with that one. This is minus 4. If I switch it, it becomes positive 4. Oh, sorry. It is 6, so it is 6, I think, yes? Am I right? Yes or no?
The fourth term.
1, 2, 3, 4 here.
Yeah, shouldn't it be minus 3v x minus 2u?
The fourth term is coming from this one multiplied by that one, yes? So it is positive, yes?
Yeah.
Yes, thank you. Yeah, yeah, you're right.
Minus. Yeah.
So let me write a minus here. But what about the rest? Did you check my calculations?
I think the last one.
Yes, the last one is the same, so I don't know why I did this. Now is it right? Yes or no? So let me double check. This one times that one is correct. This one, because I usually do them fast. When I want to write every detail, I make mistakes, yes? So I want to multiply that by that, that's correct. This one by that one is also correct. This one by that one is correct. This one by that one, now it's correct. This one, that, yes, yes, and yes. I think it's correct. So this is 0, that is 0, so therefore this one is also 0 here, because they are parallel. But let me double check here. I have U cross W here with a factor of 2. I have a factor of minus 4 here, but if I interchange them, it becomes positive 4UW, and then I have 2, so it becomes 6U times W. Yes or no? Yes, please confirm that. And then here, I go here, I have V and W. I have also V and W here, V and W there. So minus 3 VW minus VW is minus 4 VW. But then it becomes positive 2 VW, so it becomes minus 2 VW. Yes? So I considered this one, I considered that one, and I considered that one. So then what is left for me is the combination of V and U. Yes? I have only two terms. So here I have positive 6 VW, positive 2, it becomes positive 8 VW. I don't know, I have a feeling that it might be wrong. I don't have the solution here. Yeah, by the way, I have it here. So it is 6 U cross W minus 2 VW. Yes, that's correct. That is the answer. And you cannot simplify this more than that. Yes, you have to stop there. Okay, now let me give you a little bit more interesting example. So this is a simple algebra, so you need to be able to do that. So the only thing that you have to be careful is the order in which you are multiplying, because in contrary to numbers and the dot product, the order of how you multiply cross products is important. Okay, so let me write example. This is a better example. So I would say that let A, B, C, and D be vectors, be non-zero vectors. Yeah, be vectors such that A cross B is equal to C cross D, and A cross C is equal to B cross D. If A is not equal to D and B is not equal to C, show that A minus D is parallel to B minus C. Okay, so I want to give you time a little bit to think about this.
Sorry, just for clarification, it's supposed to be on the last 8V time cross U, right? And not.
I made a mistake in writing.
Yeah, it's just the last one. It's supposed to be.
Yeah, that's you. This one you mean.
Yeah.
Thank you very much. Yes, thank you. Yes, thank you very much. Okay, so I want to pause the video a little bit. This is not a hard problem. I'm emphasizing because the geometry behind cross product is a little bit complicated to visualize, especially if you have more than two vectors. So I want to emphasize that if you want to solve such a problem, I don't recommend you try to imagine it in your head. Of course, that is also a good exercise if you want to do it, but I want you to use algebra to prove something like that. So I have four vectors, A, B, C, and D. What I know is this cross product turns out to be equal to this cross product. And this cross product turns out to be equal to this cross product. And what we know is that A and D are not the same, B and C are not the same vectors. We want to show if this is true, then A minus D as a vector is parallel to B minus C. So you see that the geometry involved is very complicated if you want to imagine, yes? But using algebra makes it very simple to solve. Okay, could you solve the problem? Yes or no?
Yeah.
So how should I do that? Because my goal is to show that two vectors are parallel. I told you just in the beginning that we have two alternatives. One way is to show that one of them is a multiple of the other one. Probably this doesn't make sense that much in this context because the assumptions are about cross products. But there is another alternative to show that the cross product of these two vectors is the zero vector. Yes? Because I know that this vector is not zero, it is guaranteed by this assumption. This vector is not zero, it's guaranteed by this assumption. So if I show that the cross product between these two vectors is equal to the zero vector, then there is only one possibility, and that is these two vectors are parallel. By the way, vectors being parallel, so they can point to the same direction, the angle is 0, or they can point in different directions, the angle is 180. But in both cases, the cross product is 0, yes? So here, that is very simple algebraically. A minus D, and then you cross product it with B minus C, yes? A minus D, cross product B minus C. Yes? Then I calculate this using this distributivity. I can write A cross B minus A cross C, and then I have minus D cross B, and then it becomes positive D cross C. Yes? But then what happens here? A cross B, A cross C. Yeah, that's correct. But then I have one assumption that A cross B is the same as C cross D. So instead of A cross B, I can write C cross D. And then instead of A cross C, I can write B cross D. So it becomes minus B cross D. And then the rest of it is minus D cross B, and then plus D cross C. Yes? But then immediately you can see this one and that one are cancelled because they have different directions, and this one is also cancelled with this one, because if I interchange this, it becomes positive and they will cancel. So the answer is equal to 0. So, but A minus D is not the 0 vector. B minus C is not the 0 vector. And we know that A minus D cross B minus C is the 0 vector. So then it means that these two vectors, whatever they are parallel. Yes? So that is simple algebra. Before going to the next example, I think there are some good features in GeoGebra. I just discovered them. So let us try to visualize that a little bit. How much we are in the... Okay, so we go to this view, 3D view. Let me take graphics out, go to 3D view. Yes. Okay. And then, for example, let me take the axes away for the time being. So that's the plane. For example, that's the ground level. And then let me just draw some vectors here. So, but I have to be careful because, let me see, this is one vector, okay, and then this is vector called U, yes? So let me show the label so that we can know the name. This is vector U, and then let me go to vector V. And the size is, I don't want to make the size that big, might be, it goes up. So then let me show the label here, the vector V. Oops. So this is my vector V, yes? And now let us try to cross product them, so it will generate a new vector for me. Let me make it a little bit darker, might be. I realize that you go here and then write cross. So you see there is an option called here, cross vector vector. Yes, so you choose that option. And then your vectors are U and V. So let me write U. and then we go here, v. So that is my cross product vector, but I don't know why it is drawing it from. Of course, there is no difference, but usually I prefer to draw it from here. But it doesn't matter. What matters is the direction, okay? So, but this is a little bit out of reach now, so let me make this vector shorter. So this vector is so long that you cannot see the tip of the arrow. Okay, so let us make it a small. So if I make this vector smaller, do you think it will affect that? If I make this, the magnitude of this vector smaller, definitely the magnitude of the product would also be smaller. Do you remember? It is norm of one of them times norm of the other one times the sine of the angle between them. So let me make this u shorter a little bit. And let me also, it's not enough yet. Ah, it's coming. So I'm making it shorter, so now this appears, yes? So, okay, now let me ask your intuition a little bit to play a little bit of game. So it is clear that if I increase the size, what will happen? This will be increased. By the way, did you expect that the direction should be upwards? The right-hand rule, yes? So because I am cross-producting u by v, I don't know, they have used this fancy symbol here, but forget about it. That's just the cross product of u by v. So it means that what is the angle between u and v is this angle. So you need to bend your fingers in a way that takes u to v through the angle. And then your thumb will point upward, yes? So that is clear that it should be upwards, yes? And now, my question for you is that, what is your intuition? If I start increasing this angle, what will happen to the length of that cross product? Is the question clear? So I will try not to change the, that's actually, I don't know if I can do it or not. It is a little bit hard. If I want to rotate it without affecting the length. But my question for you is that if I can keep the length of this u and the v the same, but I will start increasing the angle if I can. I will not touch u. I want to move v around. I should be able to do that, yes? And so by doing a circle in algebra, yes? Let me just do that. This is a circle of 3 points. We have lost this circle point, yes? Do you see that circle point somewhere? We have a sphere point in a space, of course. Okay, so let me do a sphere point for the time being. This is a sphere point, but if I can find the intersection between the sphere and this, yeah, then I will have my circle. Yes, I made the trick. Yeah. Show object. Yeah, that's my circle. Yes. So I have that circle. So my question is that if I want to rotate, I will keep this the same. I want to start moving C around. Do you feel what is happening? If I start moving C around, it means that I am rotating the vector V about this point O without affecting its length. Yes. So I will not touch U. So it means the length and the direction is fixed. I will start moving C around this circle. It means that I am only affecting this angle. I am not affecting its length. Is that understandable? Now I want you to predict, before seeing the demonstration, when I start moving this around, what do you think will happen for the length of this arrow? Yes?
I think it will get longer, and then when the angle between U and V is 90, it continue moving and get short.
Short. Yes, is that understandable? So the maximum length happens when the angle is exactly 90 degrees. Okay, so let us just demonstrate. That's good, by the way, to play around with GeoGebra to learn these. Oh, but I don't know why it's affecting the size. Ah, because that is unfortunate. Yes, I understand why. So, you see why? Because that's unfortunately the point. So let me get rid of that point, if possible. Show object. And then let me put myself a point at the tip of this, and then start moving that. Hopefully this will work. Yes. Yes, but then it will not move the vector. Okay, so let me move the vector. No, it's not possible. So how should we do that then? Okay, so what I do, I will take this object away. Yes, I will do another vector from this point to that point. Then hopefully this will start working. Yes, yes, but then I have to cross product these two vectors again. Where is vector AD? Is there any name for vector AD? Do you see that? So show label. It's vector B now. Anyway, that's vector B. So let me just write one more. Cross product. Sorry. Yes. Cross product of vector U and B this time. So do you understand what I'm doing? It's not complicated. Yes? Yes. And then which one is which? I don't know. This is U and B, so let me get rid of the previous one. Yes, now I think it's okay. Yes, hopefully. This is vector U, this is vector B, this is vector U cross B, and then if I start moving this around, you see it's happening. So when I start moving thing, then it is, so as you predicted, now it is getting smaller again. You know? And then what will happen? If I go more, do you think it becomes 0 or not?
No,
It becomes 0. Because eventually this vector becomes parallel to that vector. Yes? So you see, I don't know if I can show it. Yeah. It vanishes and comes to existence in the other way. Could you predict that one as well? Yes, because now, if I ask you what is the cross product of B with U, still I am calculating, but this time the angle between two vectors is this one. I have to bend my fingers in a way that move B to U in this, through this angle. Yes? No, it is a still U cross V, sorry. It is a still U cross V. So it means that I have to calculate this. It means that I have to bend my fingers in this way. So it is down, yes? Is that right? Because I am still calculating. This vector is U cross V all the time. But before that, U cross V was in this direction, but now U cross V is in this direction. So, yes? Could you see that now? So it is important. I think it's a good practice. If you start practicing about these numbers, we will talk later. So after we finalize this part, we come back and finalize everything analytically using numbers and algebra. Okay? So about these numbers we will discuss later, but for the time being, I think that's a good idea to realize these things using GeoGebra. Yes? So I think it is a good practice if you draw some pictures and try to visualize that. Any questions here? Okay, so for the time being, let me just cross product the other way around. So this was U cross B. Let me just also demonstrate this one here. Cross product, this one, let me write B and U. Yes, so you see that they are actually pointing, they are of the same size, yes? They are of the same size, but they are pointing in different directions. Yes, exactly. And this is perpendicular to the plane of the ground. Okay. So that is a good, I think, demonstration for you to realize what is going on. By the way, I think in GeoGebra there is a nice feature. If you go to Graphics 2D, do we see something? No. Yes, you see, this is the plane on the ground now. So this is that was the circle that you saw it as a cross section. So if you go simultaneously 2D graphics and 3D graphics, in 2D graphics you see the 3D graphics on the ground. Exactly. So that is the way that we had it before. Okay, so let me just stop this. So I told you that the geometry might be a little bit hard here, but let us try to visualize the situation. Okay, that is also a good practice. What can we say about vectors A, B, C, and D? Do you think they are really hard to imagine or not? So if you try to imagine 4 vectors with that property only, A cross B is equal to C cross D, how do you imagine that? So, for example, let me have these 4 pens as my 4 vectors, and that is the tip of the arrow, okay? So here, for example, assume that this one is vector A and this one is vector B. So if I cross product A by B, it points upward, yes? So then this becomes a vector like that. Of course, not with the same size, because I have to multiply the size of this by the size of this by the angle, sine of the angle between them, but it would be something like this, either longer or shorter depending on the sizes of these two and the angle between them, yes? Okay, and now you can imagine exactly the same thing for C and D somewhere else, yes? But then if you cross product C and D, it becomes some vector like this. So then you can fine tune the sizes and the angles so that the length of this one becomes exactly equal to the length of the other one. Yes? But do you think that this is possible except this setup? So for example, can I have A and B in this plane like this on the table, and can I have C and D like that? It's not possible, yes? Because if C and D are in this plane, the cross product should be in this direction. That would be this vector, and the other one would be that vector. There is no way for them to be equal. If I want to make this cross product equal to this, then there is one way to do that, to make it exactly on the same plane. So you can still imagine if you have A cross B equals to C cross D, you can still imagine that somehow, yes? Okay. Let me now do another good example. Do you remember, I want to ask your opinion about that. Okay. Is the lesson finished?
In 3 minutes.
Okay, so let me write one example for you and then we do it. This is a very good and important example. You know that if A, B, and C are numbers, yes? Then if A times B, just normal primary school multiplication, yes? If this is equal to AC, and if someone tells you that A is not equal to 0, what can you conclude? You can divide by A and conclude B is equal to C. Yes? I want to see if this property holds for these products that we are learning. In other words, if someone tells you that A dot B is equal to A dot C, and someone guarantees that this vector is not the 0 vector, do you think that we can still conclude that the vector B is equal to C? If yes, you have to prove it. If no, you need to give me a counterexample. Yes? This is one question. The second question exactly for the cross product. If someone tells me that A cross B is equal to A cross C, and it is guaranteed that this vector is not 0, can I somehow eliminate A and conclude that B is equal to C? Yes? Try to see that if these answers are yes or no. If yes, you have to prove it. If no, just convince me with a counterexample that this is not the case. Yes? And then I will complete this exercise next week. So I will start exactly from here. No questions? Okay, thank you very much.